Gravitational Fields, narrated by Pat Bushell, illustrated by Henry Batten. By definition, a gravitational field is a region in which objects with mass experience a force. This is measured in newtons per kilogram. Originally thought as a point of attraction between masses, scientists and mathematicians, notably Pierre-Simon Laplace, attempted to model gravity as some kind of radiation field, or fluid. Today, we know it in two forms, a radial field and a uniform field. Firstly, the strength of a gravitational field is defined as a force, F, acting on a unit mass, m, in the equation G equals F over m, or ms to the minus 2. So, field type number 1, uniform fields. In a uniform field, G remains constant. A good example is Earth's gravitational field. Its field of 9.8 newtons per kilogram remains the same. This can only occur provided you do not move more than a few kilometres above its surface. Now, onto radial fields. This diagram shows them pretty simply, however it is important to remember that the arrows show the direction of force on a mass that's placed in the field, and that the arrows are never parallel or equispaced. Essentially, the field is not uniform. Therefore, as you move away from the object, the strength of the field reduces. Newton was the first person to explain gravitational fields. He came up with an equation to show the strength of a radial field. If we drew that, it would look something like this. Where little g is the field strength, big G is the universe's gravitational constant of 6.7 times 10 to the minus 11.
6.7 times 10 to the power of minus 11 what, Patch? Bananas?
M is the mass of the object that causes the field, and R, the separation between the point and the centre of the object causing the field. Now, note that G is proportional to M. That means if you increase the mass, the field also increases in size. This is represented in the equation G is proportional to 1 over r squared. This is called the inverse square law, as the field strength is proportional to the inverse of the square of the separation of the masses. Put mathematically, if you were to go x meters from the mass, the strength of the field would be 1 over x squared. For example, if an astronaut was twice as far away from the mass as his buddy, the gravitational field strength would only be a quarter as strong. We can also work out the forces acting between two fields, as we know that F equals mg. Applying this to Newton's law of G equals gm over r squared, we can deduce that the equation is F equals gm over r squared. To draw this equation out, it would look something like this.